Hi, today we will discuss sentence embedding concepts and their applications. We will learn what is sentence embeddings, why they matters, and where they are used. We will walk through some of the tools that perform sentence embeddings. We will showcase semantic similarity of various sentence embedding techniques. You can comment below how you would like to use sentence embeddings in your natural language processing projects. Sentence embeddings are dense numerical vector representations of individual sentences. Instead of representing text word by word, as we have seen in my previous videos on semantic embeddings, we encode the full sentence into a fixed length vector that captures its semantic meaning. Why they matter means sentence embeddings allow machines to compare sentences mathematically using semantic similarity like cosine similarity. The key idea is transforming sentences into a geometric space where similar meanings are located close by together. Where they are used means these embeddings are used as foundational for many NLP applications, including semantic search, clustering similar texts, question answering systems, summarization, and recommendation systems. These are very useful to design critical logic that you can apply as post processing or pre processing to your text before you pass on to LLM framework. The initial sentence embedding is developed by averaging of all word embeddings in a sentence. The word embeddings could be either pre-trained word embeddings or fine-tuned word embeddings in a corpus using methods like word-to-vec, glow, or fast text. These are the semantic word embeddings developed from 2014 to 2017, which are used in converting words in a sentence into a sentence embeddings. The process is simple: convert each word in a sentence into its vector representation and compute the average. This approach is computationally efficient and works surprisingly well for short and simple sentences. However, it ignores word order and syntactic structure. For example, sentences with opposite meanings but similar words may end up with nearly identical embeddings. Two negation sentences, such as this is a good video and this is not a good video, may have similar embeddings. This limitation motivated for more advanced neural approaches, which we will discuss next. Please subscribe, like, and comment for more technical videos. Let us discuss how you can implement the sentence embeddings using three methods called bag of word approach, turn frequency inverse statement frequency approach, and the glow vector, which is a word embedding vector used to convert the words in a sentence into a sentence embedding. And you can see that scale-on package is used to load bag of word approaches and turn frequency and inverse document frequency approaches. You can use the gensim package to load the pre-trained word embeddings of glow, and which has 50 dimensions for each word. And you can also see that we can convert 4 sentences into sentence embeddings. These are the 4 list of sentences, and you can see that the first one is directly you pass the sentences to this method, which calculates the bag of word approaches to convert the sentence into embeddings. And the second one also the same as the first one with the ID of weightage, but this will again converts the entire list of sentences into sentence vectors using this method called TF-IDF vector from the sklearn package. And the third method is called glow, which is not directly calculating the sentence embedding, but what it does is it loads each word embeddings from the pre-trained model called glow using the gensim package here. Then it will able to load the word vectors for each word and then take the average of all the words of a sentence. That will become the sentence embedding. You will get the average of all the word vector representation in a sentence will be its sentence representation. So this is the 3 methods that you can use to convert the sentences into sentence embeddings. And then we have to use the semantic similarity to see how they are similar or different for every pair of sentences from the list of sentences that we have seen. So this part will take every pair of sentences from the list and will be able to calculate the cosine similarity of each of the embeddings, and will be able to compare how the bag of word approach is different from TF-IDF approach and how TF-IDF approach is different from the glow sentence representation. So the next step we have seen here is that the plots that compares a bar chart between every pair of sentences, and then each pair you could see three methods how they are calculating the sentence similarity and how they are compared, and I can show you the results here. So this is the entire results after execution of that code. You can see all three methods have similarity. You can see the bag of words is represented this color, and TF-IDF is represented, and globe is represented, and you can compare each pair of sentences S1, S2, S1, S3, S1, S4, and the list of sentences are given here, and you can see there is no bag of word approach for S1 and S3. They will be 0. There is no words common between those two sentences, and other pair of sentences you will have all three methods similarity. And as we have discussed already, if you take the average of the globe model, then even though there is some differences in the sentences, but the average semantic similarity will be same. That is the drawback of that approach. And this you could also see that the IDF is a little bit reducing the semantic similarity between two sentences. Sentences are used as data points, and word embeddings are used as initial embedding layer of the neural network. Then either they use recurrent neural network or convolutional neural network to train sentences with some loss function at last layer, like a classification loss or similarity loss. And we will discuss those loss functions in the next slide. Recurrent neural networks, including LSTMs and GRUs, process sentences sequentially from left to right. The final hidden state is used as the sentence embedding. Because they read text in order, they capture word order and some contextual relationships. CNN based approaches apply convolutional filters over word embeddings to detect important n-gram patterns or phrases. These methods are generally faster than RNNs based methods since they are not sequential in nature. They capture local patterns effectively. These methods might be good if you want to train sentence embeddings on your own data. However, both RNNs and CNNs struggle with modeling long range dependencies compared to transformer based methods. Let us discuss a few loss functions used in sentence embedding techniques. One is contrast to loss, second is triple loss, and third is negative log likelihood loss. Contrast to loss teaches the model to make similar sentence close in meaning and a different sentence far apart. For example, I love cats should be close to I adore cats, but far from I hate cats. Triple loss compares three sentences at once: an anchor sentence, a similar sentence, and a different sentence, making sure that the anchor sentence is close to the similar one and the different one with a distance m. In the above example, I love cats is an anchor sentence that should be close to I adore cats, and I hate cats is a different sentence that should be far away at a specific distance m from I adore cats. Negative log likelihood loss helps the model pick the correct category for a sentence, like classifying I am happy today as positive emotion and penalizing wrong guesses. Together, these methods help machines capture meaning, similarity, and differences between sentences. So let us discuss converting sentences into sentence embedding using the convolutional neural network or recurrent neural network. In this example, we will be using Keras and TensorFlow for designing this convolutional neural network or recurrent neural network. We have four sentences, and we will be using contrast to loss function. In order to use the contrast to loss function, we have to define the similar or dissimilar of the sentences. So in this example, we consider sentence 1 and sentence 2 are similar, remaining all pair of sentences are dissimilar. And you can see that labels here 0 and 1, which represents the sentence 1 and sentence 2 with the similarity 1, and if other combinations you will have dissimilar, which is 0. This is the labels for our training, and you have the vocabulary size of 100 and sequence length 15, and embedding dimensions for each word is 50. So what we will do initially is you use the tokenizer method. You pass the sentences which build the vocabulary. Once it builds the vocabulary, you pass the sentences to convert each sentences into a sequence of numbers. Once you convert it into sequence of numbers, then you have to normalize them with the maximum sequence length of 15 If sentences greater more than 15 words, then first 15 words is taken. If sentence less than 15 words, 0 will be added as the end of the sentence. This is the normalization process using the padded sequences. And then you have to prepare a data for training. For that you have two sequences, sequence 1 and sequence 2, and you have labels, which is contrast to loss labels, which says whether they are similar or dissimilar. And this is the data preparation. Next you have a contrast to loss function defined here, and you have also cosine function defined here. Then you have two architectures. One is convolution neural network architecture, and it has embedding layer followed by convolution neural network layer, and followed by pooling layer, followed by dense layer. Next, recurrent neural network architecture, it has same as embedding layer followed by the bidirectional LSTM layer, followed by dense layer. These are the two architectures. You can use any one of these. In order to train this one, you need a CMS network. This CMS network is basically take two input sequences, input A and input B, and you can use any of the models, either CNN or RNN, to create embeddings. Then you have to compare those two sentences using the cosine distance as an output. And once you create this cosine distance as an output using the CMS network, then you have to use the contrast to loss as the optimizer to train the neural network. Then you will be passing the data, trained data that you have prepared earlier, to the CMS network to train the neural network. Then you will be using the same CMS neural network to predict each of the padded sequences that you have prepared earlier. That will be your embeddings. You will be able to identify the similarity between those embeddings using the cosine similarity. This method uses the cosine similarity calculation between pair of sentences. Then you will have bar chart that represents the cosine similarity between every pair of sentences that you have used in this training process. When you run the script CNN and RNN based sentence embeddings, these are the results you have got. We have used the contrast to positives for sentence 1 and sentence 2 as similar, and remaining all pair of sentences are dissimilar. You can see same results here, both the CNN and RNN giving the high similarity of 1 between the sentence 1 and sentence 2. Remaining all are dissimilar sentences, so they are not giving very high similarity for both CNN embeddings and RNN embeddings. Overall approaches have developed using transformers for sentence embedding. Since transformers introduce self-attention mechanisms, allowing models to attend the importance of every word relative to every other word in the sentence. This enables a strong contextual understanding. Models like BERT, Robot A, Sentence BERT, and Universal Sentence Encoder produce context-aware embeddings. To generate a fixed-length sentence vector, we typically apply pooling strategies such as using the CLS token representation, mean pooling across tokens, or max pooling across tokens. Transformer based embeddings achieve state of art performance in semantic similarity, retrieval, and clustering tasks, although they require more computational resources. Universal Sentence Encoder USE is a sentence level embedding model developed by Google that converts sentences, phrases, or short paragraphs into fixed length dense vectors, capturing their semantic meaning. Unlike simple word averaging methods, Universal Sentence Encoder directly produces embeddings for entire sentences, making it effective for tasks such as semantic similarity, clustering, text classification, and information retrieval. It has two main variants: a transformer based version that uses self attention for higher accuracy, and a deep averaging network version that averages word and bigram embeddings before passing them to a feed forward network, offering faster computation with slightly lower accuracy. Universal Sentence Encoder typically generates 512 dimensional vectors, allowing similarity to be measured using cosine similarity in vector space. Although new contrastively trained transformer models may outperform it on modern benchmarks, Universal Sentence Encoder remains an important and efficient general purpose sentence embedding model widely used in practical applications. Modern sentence embedding techniques often use contrast to learning, which uses contrast to loss or triple loss, in addition to modern sentence embedding techniques, allowing them to learn more on domain specific sentence embeddings. The idea is to train the model so that semantically similar sentences are closer together in vector space while dissimilar ones are pushed apart. This significantly improves performance on similarity and retrieval benchmarks. In practice, model choice depends on constraints. For lightweight systems or limited hardware, averaged embeddings may still be acceptable. For semantic search and retrieval, sentence bird style by-encoder models are highly effective. For domain specific applications, fine tuning transformer models on task specific data yields the best results. We will be showcasing that script to run the transformer based sentence embedding. We have a couple of packages here to load the pre-trained transformers. One is the sentence bot using the sentence transformers, and we will be using transformers that will be loading the bot models. And we have 4 sentence examples here. We can see the first sentence embeddings are using the bot embeddings, and we have 2 pooling concepts. One is CLS token based pooling layer, another is mean pooling layer. CLS is a special token used to separate the 2 sentences, and based on that CLS token we will be pooling the last bot layer to represent the sentence, and the mean pooling layer also we will be using to represent the sentence. You will have 2 representations of those 2 bot based embeddings, and we will be using the sentence bot embeddings here. This sentence based embeddings also a pre-trained model, and then we will be using the universal sentence encoder, which is again the pre-trained model, and we will be comparing all these 4 models using the cosine similarity on 4 sentences that we have shown before. And what it does is basically it takes the every pair of sentences and calculate the cosine similarity between those pair of sentences, and for all the 4 methods then it will compare the cosine values of the 4 methods for every pair of sentences using a bar chart. We can go and see the results. You can see there are 4 sentences, the comparison of all the 4 methods, and you will see that the CLS based BERT and mean BERT is not great in terms of the semantic similarity. They will have the same values across all the pair of sentences, whereas if you see the sentence BERT and the universal sentence encoder based representation, you have differences. The S1 S2 has high similarity compared to all other pair of sentences. That is clearly evident from these examples. So these two looks very good in this case. The key takeaways is that transformer based and contrast to learning models currently dominate because they combine contextual understanding with a strong semantic alignment.